Your hand has never touched a table. Not once in your life have your fingers made contact with a keyboard, a phone, or another person's skin. Right now, as you sit or stand, you are not touching the chair or the floor. You are hovering above it, separated by a distance so small it defies imagination, but separated nonetheless. This is not a metaphor. This is not philosophy. This is physics. And once you understand why, you will never see the world or yourself the same way again. We trust our senses completely. We believe that when we place our hand flat against a wall, we are touching it. The wall feels solid. Our nerves send signals to our brain. We feel pressure, texture, temperature. Every piece of sensory evidence tells us contact has been made. But our senses are lying. What you call touch is not contact, it is repulsion. You are feeling the force of trillions of electrons in your hand, pushing back against trillions of electrons in the wall with such intensity that the atoms in your skin can get no closer. The sensation you interpret as touch is actually an electromagnetic scream, a warning that you are approaching a boundary you will never cross. To understand why, we need to step into the world of atoms. And in that world, the rules are not what you expect. An atom is mostly empty space. If the nucleus of a hydrogen atom were the size of a grain of sand, the electron orbiting it would be more than half a mile away. Between them, nothing, just void. Yet, this nearly empty structure is what gives matter its solidity. How? The answer lies in the electron cloud. Electrons do not orbit the nucleus like planets around a sun. That picture, while popular, is wrong. In quantum mechanics, an electron does not have a definite position until it is measured. Instead, it exists as a probability distribution, a cloud of possible locations surrounding the nucleus. This cloud extends roughly 1 to 2 angstroms from the nucleus, where 1 angstrom is 10 to the power of -10 meters, 1/10,000,000th of a meter. This electron cloud is not a fuzzy metaphor. It is a real, measurable boundary defined by where the electron is most likely to be found. And here is the critical point. That cloud is negatively charged. When you bring your hand close to a table, the electron clouds in the atoms of your skin approach the electron clouds in the atoms of the table. And since like charges repel, those clouds push back hard. How hard? The electromagnetic force is incomprehensibly strong compared to gravity. According to Richard Feynman's lectures at Caltech, if you and another person standing an arm's length each had just 1% more electrons than protons, a tiny imbalance, the repulsive force between you would be enough to lift the entire Earth. That is not an exaggeration, it is a calculation. The electromagnetic force follows Coulomb's law, which states that the force between two charges is proportional to the product of their charges and inversely proportional to the square of the distance between them. At atomic distances, on the scale of angstroms, the forces become enormous. But in everyday life, matter is electrically neutral. Every atom has an equal number of protons and electrons. The positive and negative charges balance out almost perfectly, so the vast electromagnetic forces cancel. What remains are only the tiny residual forces at the boundaries, where electron clouds meet. And those tiny residual forces are what you feel when you touch something. But there is more to this story. Electromagnetic repulsion alone is not enough to explain why atoms do not simply overlap. There is a second, deeper principle at work, one that governs all of reality at the quantum level. It is called the Pauli Exclusion Principle. In 1925, physicist Wolfgang Pauli discovered a rule that applies to all fermions, particles like electrons, protons, and neutrons. The rule is simple but profound. No two fermions can occupy the same quantum state at the same time. For electrons, this means that no two electrons in the same atom can have the same set of 4 quantum numbers, values that describe their energy level, orbital shape, orientation, and spin. In practical terms, this means electrons cannot be squeezed into the same space, even if you apply enormous pressure. This is not because they are physically bouncing off each other like billiard balls. It is because the laws of quantum mechanics forbid it. If you tried to force 2 electrons with the same spin into the same region of space, the energy required would become infinite. Nature simply will not allow it. This principle is not abstract. It has real, observable consequences. It is why white dwarf stars, the collapsed remnants of dead stars, do not collapse further under their own gravity. The electron degeneracy pressure, arising from the Pauli Exclusion Principle, resists compression with such strength that even the gravitational force of an entire star cannot overcome it.
On a smaller scale, it is why your hand does not pass through a table. The electrons in your hand and the electrons in the table are forbidden by quantum mechanics from occupying the same space. The closer they are pushed together, the more energy is required. Long before they touch, the electromagnetic repulsion becomes unbearable. So you stop. You feel solid, but you have not touched. Let us consider what touching would actually require. For 2 atoms to truly touch, their electron clouds would have to overlap significantly. For their nuclei to touch, those nuclei would have to come within about 10 to the power of -15 meters of each other, a distance 100,000 times smaller than the size of an atom. At such distances, the electromagnetic repulsion becomes so extreme that atoms would rather break apart than get closer. And even if they did somehow push through that barrier, the strong nuclear force, which binds protons and neutrons together, would come into play, causing nuclear reactions or even fusion. In other words, for 2 objects to truly touch, they would have to destroy themselves in the process. And we have not even mentioned the Heisenberg uncertainty principle, which states that you cannot know both the exact position and exact momentum of a particle at the same time. If you tried to confine an electron to an infinitesimally small region of space, to force it into contact with something, its momentum would become so large and uncertain that it would immediately escape. Quantum mechanics makes pinpoint contact fundamentally impossible. So what is the actual distance between your hand and the table when you press down on it? Measurements using techniques like X-ray diffraction and atomic force microscopy show that in solids, atoms are typically separated by a few Ångströms. When you touch a surface, the electron clouds in your skin come within approximately 1 to 3 Ångströms of the electron clouds in that surface, about the width of a single atom.
You are hovering. Always. Even the floor beneath your feet is not supporting you through contact. It is repelling you electromagnetically. The sensation of weight you feel is not the floor pushing up on you in the way you imagine. It is trillions of atomic-scale electromagnetic forces acting in parallel, creating what we macroscopically call the normal force. This force is so precisely balanced that you do not fall through the floor, but it is not contact, it is repulsion. Why does our brain interpret this as touching? Because evolution did not prepare us to understand physics at the atomic scale. Our ancestors needed to know whether a rock was hard or soft, whether prey was within reach, whether fire was too hot to grasp. They did not need to know about electron clouds. So our nervous system developed a shorthand. Pressure receptors in the skin detect deformation, changes in shape caused by forces. When electromagnetic repulsion prevents your hand from moving further, your skin deforms slightly. Receptors fire. The brain interprets this as contact. It is a useful illusion, but it is an illusion. And this principle extends beyond your hand and a table. When you sit, you are not touching the chair. When you hold a pen, you are not touching the pen. When two people shake hands, their atoms never meet. Even at the molecular level, chemical bonds, the forces that hold molecules together, are electromagnetic interactions between electron clouds. Atoms in a molecule are bound not by touching, but by sharing or transferring electrons in a way that minimizes electromagnetic energy. Everything you have ever felt is a force, not contact. You have spent your entire life repelling the world around you at a distance measured in Ångströms, interpreting that repulsion as solidity, and never once questioning whether the sensation matches reality. There is one exception, one way atoms can truly come together: nuclear fusion. In the core of the Sun, hydrogen nuclei are slammed together with such violence, such extreme temperatures and pressures, that they overcome the electromagnetic repulsion and get close enough for the strong nuclear force to bind them into helium. When this happens, a small amount of mass is converted into energy, and light is released.
This is as close as nature gets to touching, and it requires the interior of a star. So here is the truth. You have never touched your mother's hand. You have never pet a dog. You have never felt the ground beneath your feet in the way you think you have. Every physical interaction you have ever experienced has been mediated by forces acting across distances so small they are invisible, unfelt, and, until now, unnoticed. But those forces are not weak. They are strong enough to hold the Empire State Building upright in the wind, strong enough to give steel its strength and diamond its hardness, strong enough to prevent your hand from passing through a wall, even though both are mostly empty space. You are a cloud of electric charge, suspended in the electromagnetic field of the universe, forever separated from everything else by the laws of quantum mechanics. You will never touch anything. And yet, the world feels solid. That is the elegance of physics. The rules are strange, but they are consistent. The universe is not what it seems, but it is exactly what it must be. If this changed the way you see the world, consider subscribing. There is more to reality than your senses reveal, and we are just getting started.